Hello everyone, my name is Petrovska. I'm coming from the Technical University of Munich, and I'm pleased to have this opportunity to talk about some preliminary results on my research on runtime multi-agent knowledge aggregation with subjective logic in self-adaptive cyber-physical systems. Modern systems, such as cyber-physical systems, are composed of many interacting and interconnected components while inheriting all the complexities of modern large-scale distributed systems, and they deliver complex functionalities. Additionally, their close connection to the physical world means that they are exposed to high uncertainties during their operation. Namely, modern cyber-physical systems need to be able to operate efficiently and reliably within a continually changing, uncertain, and unanticipated environment or execution context. Often, they need to cooperate and collaborate with other cyber-physical systems to provide shared functionality. A common approach to deal with runtime changes and uncertainties that could not be fully anticipated during the design of the system is to make the cyber-physical system self-adaptive. Self-adaptation is traditionally realized by an adaptation logic based on the closed feedback loop MAPK. I'm sure all of us are familiar with it, with four consecutive functions: monitor, analysis, planning, execution with shared knowledge among all the elements in the loop. The knowledge component comprises models of the cyber-physical systems and the context in which the cyber-physical systems are operating. Due to the dynamicity of the cyber-physical systems and their execution context, these models cannot be created based on assumptions made at design time, but instead they need to be models at runtime. Concretely, the runtime context model should get continuously updated in response to the changes in the context, reflecting the actual operational context during the execution of the cyber-physical system. To update the model and accordingly the context, the knowledge component, the need for runtime information, aggregation, and reasoning of what each cyber-physical system individually observes emerges. In our work, we focus on self-adaptive cyber-physical systems in which MAPK loops are structured according to the master-slave pattern previously proposed by Vance et al. Briefly, the description of the pattern is the following. So one or more MAPK loops at a lower level perform decentralized monitoring and execution of the adaptation actions. However, centrally, there is a single high-level MAPK loop that performs analysis on the monitor data, updates the knowledge, and does the planning accordingly. In our focus are multi-agent cyber-physical systems, we assume that every cyber-physical system has the ability to monitor and execute actions. However, the analysis phase needs to reason on the uncertain, inaccurate, and potentially conflicting observations coming from the decentralized monitoring, which once aggregated, the observations become knowledge. Knowledge aggregation is essential since it can have a significant influence on the subsequent phases of planning and executing. However, knowledge aggregation is challenging since, as mentioned above, it needs to take into account the inherent uncertainties related to each monitor and provide ways to synthesize and consolidate the observations. The identified problems, to sum up, are runtime uncertainties that arise due to continuous changes in the multi-agent operating context. This can be internal uncertainties coming from the sensors of the cyber-physical systems, usually as noise, ambiguity, imprecision, even sensor failure, and external uncertainties coming from the unpredictable environments or contexts where the cyber-physical systems are operating. Also, the conflicting context observations among multiple agents, if they are left unresolved, then this leads to suboptimal decisions. Although knowledge and its aggregation is an important concern for MAPK, there is a scarcity of approaches for modeling knowledge in a self-adaptive systems that allows capturing uncertainties at a local level and for a later effective decision making based on the aggregated knowledge at a global level. Instead, knowledge modeling is typically treated as a domain-specific task leading to ad hoc solution to knowledge aggregation. As a response, in this paper, we present an approach for observations, aggregation, and knowledge modeling in self-adaptive cyber-physical systems that is domain-independent and can deal with reasoning on inaccurate, partial, and conflicting observations. Concretely, our approach uses subjective logic to build the knowledge by aggregating observations of the context made by each agent in the decentralized multi-agent self-adaptive cyber-physical systems. We also propose an open-source implementation of a RAW-based multi-agent system, further explained in the next slides, to demonstrate and evaluate the proposed approach. Let's dive into the running example. The reference problem is comprised of several cleaning robots operating in the same context, for example, the room. Each robot is able to autonomously move to a destination while avoiding the static obstacle, walls, furniture, and the dynamic obstacles, which can be other robots and humans along its way. New dirts continuously appear in the room, and it's important to point out that the pattern in which the new dirts appear are not known during the design of the system. The robots discover the tasks in a distributed manner with LIDAR sensor. The robot's observation space is determined by the scanning distance of the laser scanner, which is less than the room's dimensions. Hence, each robot can observe only partially the room in which it operates. Consequently, the robots can detect the newly appearing dirt tasks only if they're within their range of observation. The mission of the robots is to keep the room as clean as possible by discovering the dirt tasks and then cleaning them in the most efficient way. However, the fact that the robots have only partial observations of the room brings inefficiency to the overall performance. For example, when one part of the room is getting dirtier than the other. And we can see here on the figure, from so many tasks there, the 3 robots are at this time able to identify, to monitor, to observe only one of the tasks. We model the context as a grid map with a size equal to the size of the room. A context variable models whether a specific cell of the grid map has a dirt task or not. So there are as many context variables as cells in the map of the room. Therefore, the partial observations made by each robot are sent periodically to the cleaning controller, whose responsibility is to aggregate the received observations and assign the discovered dirt tasks to the robots while respecting the optimality criteria mentioned above. Once when the dirt is assigned to the robot, the dirts go and cleans it. The multi-robot cleaning system is subject to external, contextual, and internal or system uncertainties manifested with the continuous appearance of dirt in the room and different sensor certainties respectively. Occasionally, each robot will mistakenly sense a dirt task when there is none, and on the contrary, fail to sense an actual task. This potentially leads to conflicts in their observations. Few words on few slides, as brief as possible, on subjective logic. More recently, subjective logic theory has gained a prominence because of its capability to deal with the uncertainty of observed events. It explicitly represents the amount of uncertainty on the degree of truth about a proposition and provides operators to combine opinions from multiple sources. Subjective logic can be seen as a framework for artificial reasoning in which the general idea is to enrich the probabilistic logic by including uncertainty about the probabilities and subjective belief ownership. The fundamental building block of subjective logic is subjective opinion. An opinion expresses a belief about the state of a variable which takes its value from a domain or a state space. The domains in the subjective logic can be binary or an array. Binary domains are typically used when modeling situations that have only 2 alternatives, such as the case in our running example, where the location in the map of cell can be either dirty or not. A binomial subjective opinion is a function, omega, where the respective parameters are defined as following. Bx is the belief mass in support of x being true. Dx is the disbelief mass of support of x being false. Ux is the uncertainty mass, and Ax is the base rate, for example, the prior probability of x without any previous evidence. Opinions with Ux equal 1 are called vacuous, and Ux equals 0 are called dogmatic. The adaptivity requirement needs to be satisfied as shown on the slides. Bx plus dx plus ux needs to be 1, and the expected probability of the binomial opinion about the value x is defined by the last formula on the slides. When there are more than one opinions for a proposition, there is often the need to merge and combine them into a single collective opinion. In subjective logic, this is realized through a process called belief fusion. So, for example, you can see on the figure we have multiple robots. All of them have their own opinion, then that are later on merged into a single opinion. Subjective logic provides a variety of operators, generalizing and extending operators from binary logic and probabilistic calculus. In our work, we have chosen to focus on two: cumulative belief fusion, CBF, and consensus and compromise fusion, CCF. If someone is interested why and how we chose these two fusion operators, I'm more than happy to address this question in our discussion session. Very briefly, why CBF was a good fit for us. So it's helpful when we are accumulating partial observations that help us increasing the confidence in the dirt detection, and the consensus and compromise fusion is helpful when we are resolving conflicting partial observations. As discussed in the motivation, in our approach, different MAPK loops are structured accordingly to the master-slave pattern. In particular, there are several decentralized monitor and execute components located in each robot, and single centralized analysis and plan, as you can see in the figure. The monitors in each robot make independent observation from the context. However, these observations are partial and only cover part of the context, and they can also be incorrect if they include mistakes due to the sensor noise and ambiguities. Each monitor has a subjective opinion creator entity, which is responsible for creating the subjective logic opinions from each agent about different context variables. Once the subjective opinions are created, they are propagated to the knowledge aggregator. The analyzer is a centralized component in our approach that collects and aggregates the subjective logic opinions from the distributed monitors and updates the runtime context model in the knowledge component. The planner is another centralized component in our approach that is responsible for selecting of the adaptations or plans, which are later being executed by each of the lower level MAPK loop. We assume that the planner relies on the runtime context model, represented by the context variables, and we, in our approach, we don't prescribe how we perform the planning. So it can be any planning approach, rule-based, goal-based. However, in our implementation of the multi-agent system, from our running example, we have implemented an algorithm for self-adaptive routing in which the robots bid for a task and adapt their task queue at runtime. But going in more detail of the bidding algorithm, it's out of the scope for this paper. And finally, the executor component obtains adaptation actions or plans from the planner and independently executes them. The figure depicts the partially, now we dive in a bit deeper into subjective opinion creators. So the figure depicts the partially observable context, its grid map model, the three deployed robots with their detection ranges in blue circles. The robots deployed in the room are able to detect the objects and the newly appearing dirt only if they are inside their visibility radius denoted by R. A robot, for example, R1, issues a subjective opinion for each cell in the grid map, and that is within its range R. Consequently, the following information is omitted from the paper for space reasons. However, each grid cell contains N on N so-called point clouds. However, how many points are in the cell depends on the map's resolution and cell size. The opinions that the robots issue for each cell, concretely each point, depend on the Euclidean distance d from the robot to the cell or the point, and models whether that cell contains dirt or not. In particular, the parameters are calculated accordingly to the following formulas. The further a cell is from the robot, the higher the uncertainty mass of the robot's opinion. Observations at the edge of the leader sensor's range or the sensor border are considered highly uncertain, but can still contribute during the knowledge aggregation. Hence, we assign uncertainty value to them of 0.99 instead of totally uncertain opinion. The base rate is always considered to be the default base rate for a binary domain 1/2. The knowledge aggregation takes place each time a robot informs the knowledge aggregator of a made partial observation of the context. For the cells covered in the partial observation, subjective opinions are issued. Additionally, the knowledge aggregator extracts the previously stored opinions on those particular cells from the knowledge, and for each cell, both of the opinions, the current and the past, are then fused and aggregated, and the runtime context model in the knowledge is updated accordingly. As an example, here we can consider situation as depicted in the figure, where two robots hold overlapping a partial observation and a third cell, in this case depicted by the star, is detected. When the knowledge aggregator receives the independent partial observation sent by the robot, it initiates the aggregation process. Let's consider two scenarios. In the first scenario, both of the robots agree on the dirt in the same cell, and in the second scenario, they disagree. For example, R1 does not detect a dirt that R2 detects. Following the formulas showed above, we calculate the values in this table. I won't go very much into details, but I will just mention that in both scenarios we can observe improvement in the confidence of the aggregated observations, which is a reducement of the uncertainty mass, here depicted with blue color. Okay. Few words on the implementation and the preliminary results. So in our implementation, the entire communication is based on ROS. For simulating the robotic system, we use Gazebo, and the robots we simulate are Turtlebot 3 burgers. Gazebo relies on well-established physics engines, which enables high physical, functional, and visual fidelity. Simulations with high fidelity closely resemble the real world, meaning that the model and even the physics of the robots, the environment, including the static and dynamic objects, are simulated as realistically as possible. With our implementation, one can simulate as many robots and in different given rooms. Additionally, the software that exists in a simulation can be deployed on a real robot without any modification. The source code of the implementation is open source. To evaluate the knowledge aggregation approach, we conducted 5 series of experiments, 10 minutes each. For the simulation of the appearance of new tasks, we used a random seed in each experiment, and to guarantee a better replication of the test scenarios, we used a fixed frequency with which the new tasks were created. To compare these results with the base scenario, so we compared the results from the base scenario, where there is no aggregation, with aggregation with CBF and CCF. We use 3 metrics to evaluate our results: the average time that the robots need to discover a task, the average time that the robot needs to attain a task once the task is discovered, and the total time including the discovery and the attainment. In our preliminary experimental results, we see that the discovery time increases for both CBF and CCF, and this is expected since they need more time and evidence to discover tasks and create cleaning goals from those tasks. However, the total time increases, although we expected the opposite. Even if we have increased the sensor noise, there was not a drastic change in the results. So our question was, okay, what went so wrong? Why are the results so counterintuitive and different from what we initially expected? The main issue that we could identify is that the Gaussian noise affects only the range of the sensor beam, and it was not producing false observations within the sensor range. With this, we could not prove our main hypothesis, which was using the subjective logic for solving conflicts caused by false positive, meaning tasks being observed when in reality they don't exist, or false negatives, tasks not being observed when they in reality exist, or tasks observed in position that deviates from their true position within their sensor range. So our work was really theoretically heavy, including understanding the subjective logic, and also implementation heavy. Whoever has worked with ROS knows the pain of it, and also it was further amplified by the multi-agent nature of the system. And I think we kind of got lost in all of this, which resulted in us overlooking the false observations, which was one of the main motivations behind the work. Without being aware of this problem, we did an extensive evaluation considering many setups, number of robots, and we discovered these issues while interpreting the results, where it was really more than visible that something went very wrong. Unfortunately, this happened quite close to the deadline, and that is why adding false positive and false negative would have taken weeks also to do the re-evaluation, and that is why we went for short paper instead. Another comment for showing the effectiveness of the aggregation with subjective logic, we needed to have realistic sensing, just how a real robot would sense its environment and discover the tasks. In other previous work, I have worked with mocked sensing, and their modeling and adding the sensor noise or the false observations was much more simplistic compared in our case. To sum up, in this work, we proposed an approach that uses subjective logic to collaboratively aggregate the partial observation of the context made by each robot in a multi-agent setup. Accordingly, the runtime context model in the knowledge and adaptation logic is updated, which is later utilized by the adaptation logic to analyze and plan the next adaptation actions. The provided use case and implemented testbed set the basis to experiment with different methods for knowledge aggregation and adaptation. The future work, and all of them are work in progress with the exception of the third point, is adding false positive and false negative to demonstrate the effectiveness of solving conflicts with subjective logic, conduct more thorough evaluation in different setups, varying the number of robots, the room maps, and the amount of false observations, automatic selection of the aggregation observations, so we had only manual selection here, but are there ways for us to figure out how this can be done in an automatic fashion, and also, quite important and interesting, investigating how other logics perform in comparison to the subjective logic. For example, belief revision or other non-monotonic logics. Thank you very much for your attention. I hope you enjoyed my talk, and I'm looking forward to our discussion and meeting you all, even virtually, and I wish you all a very pleasant day. Thank you.